Hello everyone. Today we will be covering static and dynamic balancing. This will be, I believe, the last topic in force analysis before we get into cams. So we'll start with static balancing and then we'll get into dynamic balancing. I'll talk about the applications of each of these. These are both pretty common. Basically anything we have something rotating and we want to minimize the shaking forces, we need to balance it. Okay, static balancing. So we've talked about shaking forces and moments, and we saw that the shaking forces could be quite large. If we have, essentially, if we've got something that is, like if I have a pendulum that's spinning about some fixed point and the center of mass is offset from the center, as this thing rotates around, there'll be a shaking force. So anytime I have an eccentric weight, there's going to be a shaking force, and I need to try to balance it if I want to reduce those shaking forces. This is going to go up, the forces usually go up with omega squared, as we'll see when we get into the math. So as things go faster, the need to balance increases drastically. If you did not watch the video from the shaking forces lecture, please go back and watch that before you go on, and that will illustrate balancing in something like a washing machine that's got a drum that rotates fairly quickly, and it might have eccentric loading. Just because when people throw in a whole bunch of jeans or towels or something in there, they might all wad up and you have an offset mass. And those washing machines will actually have a mechanism to sort of counter that balance. They'll have some kind of a counterweight that will try to balance the load as it spins around. It might be spring loaded, it might be something else, but at some point in time it might get too overloaded and shake itself to the point where I've seen washing machines hop across floors sometimes. Because they're unbalanced. But there's a lot of other things that need to be balanced too. We'll talk about that in a bit. So the process of reducing the shaking forces and moments is called balancing. That's what we're doing in balancing, is we're reducing shaking forces and moments. So any link in a mechanism that undergoes pure rotation can and probably should be balanced. It's usually fairly cheap to do. Especially as things start spinning fast. The faster they spin, the more of an issue this becomes. Again, omega squared, so it's not linear. Two major kinds. There's static, which is a single plane balance, and dynamic, which is a multi-plane balance. In a static balance, we're just getting rid of forces, but we're not doing anything about moments. In dynamic balance, we're getting rid of the forces and moments. You'll see why that's important in a second. So, what's something you use every day that has to be balanced? Things like tires, right? Whenever you get a new set of tires on your car, they need to be balanced. Why? Because the rims that you mount tires on aren't perfectly manufactured. The tires themselves aren't perfectly manufactured. And when you put a tire that's imperfect on a rim that's imperfect, you put it in a random orientation, there's going to be some unbalance. The center of mass of the system is not going to be at the point of rotation. So when you spin it, there's going to be some unbalanced force that's going to try to shake it. Now in vehicles, I've driven a lot of race cars that have tires that aren't balanced, that run a relatively low speed, things like Formula SAE cars. In that case, we never really balance the tires, and it's not that big of a deal, again, because that omega squared thing. So, if you tried to run on just a regular vehicle, or your car or truck or something, on unbalanced, you put the tire on the wheel and drive around. In most cases, it would probably be okay, and it might just be a little uncomfortable at higher speed and vibrate a bit. For really big imbalances, like really big tires at low pressure, it might be more of an issue, and it might be, instead of being an inconvenience or annoyance, it might actually end up being a safety concern. But it's just a good practice to balance things if you can. Even if it's not going to be a huge deal, you might as well balance it anyway because it's so easy to do. If there's some things that have to be balanced or they'll tear themselves to pieces, turbocharger impellers can spin hundreds of thousands of RPM. For smaller ones, for bigger ones, it might be 10 or 20 or 30,000 RPM, but it's big enough that any imbalance will cause it to tear itself to pieces. Big electric motors, like big induction motors, industrial induction motors, like a 100-horse induction motor weighs about 3,600 pounds, if I remember the motors correctly. And the rotor in that's probably somewhere, I don't know, maybe around 1,000 pounds of that, spinning at up to 3,600 RPM. If that thing's not balanced, it is going to do bad things. So there's lots of applications where you have to balance things. I worked at a fan company where we made big industrial fans that had like 36 to 48 inch rotors in them. And those things would definitely need to be balanced. Every single fan that went out was balanced, at least the bigger ones. And you could see, maybe a half inch of tolerance in the different parts of it as it was spinning. You'd see it look like it was wobbling, but it wouldn't shake because it was balanced. So, basically, anything that spins, especially things that spin fast, we should probably balance them. Things like CDs and DVDs need to be balanced, which we're getting to the point where people don't even know what a DVD is. So the world's changed a lot in the last 20 years. But DVDs and CDs spin very quickly and need to be balanced. So the easiest kind of balance is the static balance. We're essentially going to balance things in a plane. So the name's sort of it's not a great name because it applies to non-static bodies. It applies to rotating bodies. But the easiest way to think about a static balance is I have some object. So let's have some kind of a disc here. I'm going to put a bearing in the center of this thing and spin it. I'm going to look down that axis. If the center of mass of the object is not on the axis of rotation, it's not balanced. What we do in a static balance is we simply move the center of mass on top of the axis of rotation. So what separates this from a dynamic balance is we don't really care what's going on along the axis, and that we don't care if we look at this from the side. So if I look at this from the side, if the center of mass is here, we're going to move it down to the point of rotation, but we're not going to care about where we move it in this direction along the axis of rotation. So, and we'll see why that matters later on. But for now, the easiest way to think about a static balance is we look down the axis of rotation and we move the center of mass of the body on top of that. So how do you move the center of mass of the body? Well, there's a couple different ways you can do it. You can remove material or you can add material. So the easiest way, and what we'll talk about, is adding material. So essentially I need to add material 180 degrees out of phase with the imbalance to counter that, and the sum of the composite body of the original body plus the weight I add, the center of mass of that composite body will be at the point of rotation and it will be balanced. That's really all we're doing with static balance. It's really pretty easy to understand, and the math ends up being pretty simple too. This will only cancel out inertial forces. So to do a little bit of derivation on this, we've got F equals ma, we've got our external forces, and you can think of the right-hand side as the inertial forces. For static balance, we want these all to be 0. We don't want any inertial forces. So we've got a little diagram here. We've got our link that's got a center of mass that is not at the point of rotation. Point of rotation is here at the origin of our coordinate systems. We're going to assume a constant angular velocity. Turns out that's actually a pretty good assumption. With constant angular velocity, the only acceleration will be the centripetal acceleration, right? The omega squared r term that's going to point towards the point of rotation. We're going to put centripetal acceleration for the body that we're trying to balance and some theoretical balancing weight we're going to add. So this is the thing we're trying to balance. This is the piece of whatever we're going to add to make it balanced. Now, we're going to assume there's no external forces on this thing, so we're just going to cancel out the forces due to the inertial forces of the center of masses being slung around in a circle here, and the centripetal acceleration of those centers of mass. So we just have minus mass times acceleration equals 0 for each of our weights. So acceleration for each of these is just going to be omega squared r. We got a whole bunch of minus signs here that don't really matter, right? Because I can divide through. Actually, they cancel each other out anyway, but I can just get rid of all of them because the right-hand side 0. And I just get an m omega squared r term for each of these. Note also that omega squared divides out of this too, which means that our original assumption of assuming constant angular velocity is good, because it doesn't matter what speed we balance at. As long as we balance it at one speed, it will be balanced at another speed, as long as we're dealing with rigid bodies. That's important. Compliant bodies that change shape as they spin faster, the balance will change, and that could be an issue. All right, so anyway, the end result is all the minus signs go away, all the omega squareds go away, and we're just left with this. And basically, this is mathematically exactly what I said earlier. This is our left part of this is our original imbalance, which is mass times the center of mass location for the CG of the thing we're trying to balance. And then we need to add something on there that is the mass of the balancing weight in its position, and these things are going to be equal and opposite of each other, those quantities, the m times r. So I'm going to go through and derive some equations here for calculating static balance, but really you don't need to do that. All you need to do to statically balance something is find the CG of the body you're trying to statically balance, add a weight that is in the opposite direction, and M times R for the balancing weight has to be M times R for the CG of the thing you're trying to balance. And as long as you do that, it's balanced. So again, I'm going to do all this math here, but you don't need to do it. All you really need to do is put a balancing weight 180 degrees out of phase with the CG, and M times R for the balancing weight is M times R for the thing you're trying to balance. That's all you got to do. Alright, so we'll do the math on it. So we're going to split this into X and Y components. We're going to find the angle for our balancing weight. That's going to be arctan of the Y and X locations of the balancing weight, right? That's just from definition of tangent. We're going to take these equations here, so RBY, RBX, we're going to multiply both by MB, and so we get that. You can probably see where this is going, right? I've got an equation that's got MB, RBX, so I can sub that in. So we're going to sub the right-hand sides in for each of these. Remember, for arctan, I cannot get rid of these minus signs. It's real tempting to get rid of those minus signs, but that breaks arctan. Remember, arctan, you need both the numerator and denominator to keep things correct. You're really going to make a huge mistake if you get rid of those minus signs in the arctan. Note that mass is going to divide out on this, and so we're simply left with the angle for our balancing weight is the arctan of the negative of the y coordinate for our CG of the body we're trying to balance, the negative of the x coordinate of the CG of the thing we're trying to balance. Again, all this is saying is this is giving us an angle that's going to be 180 degrees out of phase with theta here. That's all this is going to do, and then really it's just these minus signs in here. So again, you can use this equation, it works, but just find theta and add 180 degrees. That's all you need to do. As far as finding the position, we can use the magnitude equation, right? So r squared is rx squared plus ry squared. We can use that, and we can multiply both sides by mb. We can factor mb inside the square root. We can distribute it to these two terms. I can pull the square root out of each of those, and then I can replace mb/rbx with mrcgx. And now I have an equation for, given the mass of the thing I'm trying to balance, which I have, and the CG location of the thing I'm trying to balance, which I have, I can find the quantity mb/rb. Now I can't separate this. I can find what mb times rb is equal to, but I can't exactly find mb and rb. Turns out there's an infinite number of ways to balance something statically, dynamically too, but for now statically there's an infinite number of things. Really all we need is mb rb equal m times rcg. Anything that satisfies that will balance it, which means I can make more mass for my balancing weight and less distance, or I can use less weight and put it further away. I just need this mb rb to be the same as the mass of the thing I'm trying to balance times rcg, and if I do that, it will be balanced, and if the angle is the correct angle. So there's choices, so I can use a lighter weight farther away, or a closer weight, or a heavier weight closer. Again, you can go through and use these equations, but it's easiest to just find theta at 180 degrees and then use mb/rb, mass of the balancing weight, times the radius of the balancing weight, the radius to this, so from the origin to where the balancing weight is at. That has to be mass of the thing I'm trying to balance times the distance it is away from the axis. And as long as you know those two basic things, the angle and the magnitude, you can balance anything statically, and you don't have to go through all of these equations to do it. So here's a little problem here with some numbers in it. I use the equations in this, but again, I'm giving you the angle 40 degrees, so where should the balancing weight be? At 180 degrees, it should be at 220 degrees. How far should the balancing weight be away? Now in this case, I don't tell you either MB or RB. So this would be more of like a design problem where you are trying to balance this thing on your own. In this case, it weighs 20 kilograms. The center mass is here at the center mass is at half a meter. You want to balance this. So again, there's an infinite number of ways of doing this. As long as you put your balancing weight over here at 220 degrees, Anything that it MBRB is M times RCG. Anything that satisfies that works. So in this case, this is 20 kilograms times 0.5 meters. So anything that satisfies that 10 kilogram meters works. So I can put 10 kilograms at a meter. I can put 20 kilograms at half a meter. Anything that satisfies that is fine. So I need to go at 220 degrees, and I need mass times radius from the balancing weight to be 10 kilogram meters, and it works. So here I'm using a 40 kilogram balancing weight, and I need it to be a quarter of a meter away. Again, so there's options for this as far as how far or how heavy your weight can be. So if you want to make something light, you put something light far away. If you want to make something compact, you put something heavy closer. A lot of different ways to solve this. Easiest one is to just add 180 degrees to the angle from the origin to the CG of the thing you're trying to balance, and then use MBRB equal to M times RCG, and that's by far the easiest way. So what does static balance work for? Static balance works for thin things. So something like a CD that's relatively skinny, if I think about where the CG can be in that, it's got to be somewhere in the two planes of this thing, right? I can't have a CG outside of those planes. But there's just not a lot of wiggle room for the CG along this axis, this direction. So for things that are relatively thin, a static balance works pretty well. So for something like a CD, a DVD, maybe a bike wheel, something like that, a static balance would be fine. For something like a crankshaft and an engine, that's not fine, and we'll see why in just a second. All right, dynamic balance. Dynamic balance is for balancing the shaking forces and shaking moments that result from the shaking forces. With static balance, we can add a minimum of one weight, and we can balance anything with static balance. Dynamic balance, there's some shapes that are perfectly set up where I can add one mass, but in general, for dynamic balance, we need to add at least two weights. With just two weights, we can pretty well dynamically balance any rigid body you could think of. And I say pretty well. Theoretically, you can balance any rigid body dynamically balance any rigid body with two weights. There's some things where the geometry is not right, and there's no place to put the two weights that you need to, and you might compromise it or do more than two weights. But in general, we add two weights. Like when you balance your tires, when the mechanics balance your tires at a tire shop, they put two weights on there. That's dynamic balancing. You can always do it with two weights, theoretically at least. So anything that is relatively long about the axis of rotation should probably be dynamically balanced. And I'll put a diagram up here it'll make sense on it. So let's look at this example here. So looking down our axis of rotation, so the axis of rotation would be the z-axis. These are my x and y axis. I've got two different bodies here that are rotating on a common crankshaft. One's here and one's here. Now let's say they have the same mass, right? So if this is 10 kilograms, this is 10 kilograms, and I spin this thing and it's rigid. Now this would be statically balanced, right? This guy would cancel out this guy. There would be no forces in the XY plane, and it wouldn't do it. It wouldn't shake, right? Well, wrong, right? If they're spaced along the z-axis, then this guy is going to be, as it rotates, it's going to be trying to pull the shaft up that way. This guy, as it rotates, it's going to be pulling the shaft down that way, and there's going to be a net moment that's going to make this thing rock, and that's going to rotate as it goes around. And so there's going to be a rotating moment, and it's going to cause this thing to wobble around the axis of rotation, and that will cause it to shake. It's going to be wobbling as it rotates. So even though there's no net force in the XY plane, there's going to be a net moment, and that net moment is going to rotate, and this thing is going to shake. So how do I balance this thing? Well, you can see I can add two weights to this system and balance it really nicely, right? I can do this and I can do that and put two weights that are identical to those, and then it's nice and symmetric and balanced, and it won't have shaking forces and it won't have shaking moments. It's essentially what we're doing with dynamic balance, is we're going to add two weights. We just want to do it for any arbitrary collection of bodies. Things that are dynamically balanced, crankshafts. and engines are going to be dynamically balanced. Camshafts are going to be dynamically balanced. Axles are going to be dynamically balanced. Drive shafts. Some gears, electric motor rotors will definitely be balanced. Turbines of all kinds will be balanced. Prop shafts, that's a drive shaft. Tires and wheel combinations, those will be dynamically balanced. Basically anything that's relatively long about the axis that spins relatively fast will be dynamically balanced. It's pretty easy to do after you've manufactured something too, as long as your tolerances are somewhat decent. We'll cover two different ways of doing this. The first would be more useful from a design perspective when you're designing a system to design something to be dynamically balanced. The second method is more once you've made something and you want to balance it, how you do that, which is force-based balancing. So this dynamic balance will be for lumped masses, mainly useful for design, not super useful once you've actually made something. As in, it's not useful at all when you've made something and want to balance it. So of the things we cover today, force-based dynamic balancing is probably the most common and most important. All right, so anyway, we'll get through a lumped mass here, and then we'll get into the interesting stuff with force-based. So here we've got 3 bodies, and this works for an arbitrary number of bodies. They're all on a common crank spinning about the z-axis, and we've got their various z locations. We're going to add 2 weights to balance this thing. We're going to add this weight and this weight to dynamically balance it. Before we add those weights, we're going to define 2 correction planes. This will be true for force-based balancing too. So these will be the planes that I add these weights on. You want those planes to be separate from each other. You don't want them to be close. Now theoretically you can put them just very, very close to each other and balance it. You can't put them on top of each other, and you can put them wherever you want along the z-axis, but in general you want them to bracket the CG of the things you're trying to balance. So all of our CGs, the thing we're trying to balance, are here. So we really want to bracket those with our planes. So we could put our planes here, and that would make sense. You usually put your planes somewhere where you've got material to add or remove. So like on a crankshaft, you usually balance by removing material. Maybe you add material. You got to have some material there to remove, which would be negative mass. You've got to have some place where you can add material, right? You've got to have something there that you can drill a hole and put a dense weight in, a material that's denser than the material you remove. Like, you could put a tungsten weight in a crankshaft to balance it, or a uranium weight too if you want to spend a bunch of money and be mildly radioactive. But I need to have, like on a wheel, or you've got to have, your balancing planes are going to be at the lip of the wheel shell where you can clamp a weight to this thing. So these correction planes are usually limited by where you actually have some material to remove or a place to clamp on or add additional material. All right, we're going to use one of the correction planes to define the origin of our z-axis. So we'll use the A plane to define the origin of our z-axis, and we'll measure all of our z-coordinates from the A plane. Applying a force summation to this, we're going to assume no external forces. We're just going to balance the inertial forces. And so we've got the mass of each of our weights times the acceleration. Remember, the acceleration is centripetal acceleration for each of these things. So the magnitude will be omega squared r. So we have mass times acceleration for every single one of our weights here, all added up for this system of weights. We get rid of all those minus signs. Note that omega squared divides out. That's good. That means that dynamic balance is angular velocity independent, which means we can balance at 1 RPM and it'll be balanced for all RPMs, assuming it's a relatively rigid body. So get rid of all of our omega squareds. We can get rid of some minus signs here. We can put our balancing weights on one side, all the stuff we're trying to balance on the other. If we had more things we were trying to balance, this just gets longer. Split these into components, look at equations and unknowns. So I know all of this stuff. This is all the geometry and mass of the thing I'm trying to balance. This is the stuff I'm trying to add. How many unknowns are there? 1, 2, 3, 4, 5, 6. There's 6 unknowns. The masses and the positions of each of those. How many equations? I have 2. I'm down 4 equations right now, so this is not going to work. So we're going to do a moment summation. We're going to do a moment summation. So this is going to be the moment created by, so as these things try to sling away from the shaft here, that's going to be this moment about the, in this case it'd be about the x-axis. here, and there'd also be a moment about the y-axis too, because these aren't going to all be in the align with the y-axis too. So essentially these are going to be the moments about the x and y-axes, not the moment about the z-axis. Moments about the x and y-axes, the rocking moments of these things. Now the a balancing weight is the ZA is 0, so this term actually goes away. I need to know the z coordinate for each of these planes, so I need to know how far along the z-axis is this guy, how long on the z-axis is this guy, how long is this guy, and the distance between our A and B planes. Again, we're going to lose this term. We're going to get rid of all these omega squares. This simplifies down pretty nicely. The moment summation does. Collect all the stuff we know, which is mass times radius, or sorry, position vector, right? It's still a vector, times the z coordinate. So this will be all geometry and mass for the stuff we're trying to balance. This is for the thing we're trying to add, to balance it. Remember, by putting the origin of our coordinate system on the A plane, we lose this term, so we just have something to find the location of the B balancing weight. This gives us two equations. What are they? The x and y components of this. So now we have two more equations to work with. The x and y moment summations. So we have 2 force, 2 moment. How many unknowns? We have 6. So now we're down to 6 equations, or 6 unknowns with 4 equations. So summarizing those 4 equations, here we go. We got our 2 force and we got our 2 moment. There's not going to be any more equations. So what that means, if we have more unknowns than equations, then our system is underdefined and there's an infinite number of solutions to this. That's actually not a bad thing in this. So we satisfied our 2 necessary conditions for this being no forces and no moments. That's what we're really trying to do, is no forces and no moments. If we just used these 2 equations and went ahead and found MA, MB, RAX, RBX, RAY, and RBY that satisfied just those 2 equations, it would be a static balance. If we find a combination of those parameters, those 6 unknowns, that satisfies both these sets of equations, then it will be it'll cancel both the forces and the moments, and it will be dynamically balanced. So any combination of unknowns, the MB, RB, MA, RA, and we've already defined the Z locations of those, so that's on the right hand side here. So any combination of these things that satisfies these 4 equations will be dynamically balanced. Again, we have a choice, and essentially what that choice is going to be is mass times radius for these 2 things. Just like with static balancing, we could pick the mass and then find the radius, or pick the radius and find the mass. Same thing works here. And that's really going to define our last 2 equations, would be that MB times RB is going to be a constant for these. So here's a quick example of doing lump parameter or lump body dynamic balancing. All we've got is the position of all these weights we're trying to balance. We have their masses, we have their Z locations given here, and we want to balance this. So I need to get these things broken into x and y components. I need x and y for all of our vectors. Do the moment summation first. For dynamic balance, we always look at the moment summation equations first. Why? Because we'll be able to figure out everything about the B balancing weight, and then we can go back to the force equation and figure out what's going on with the A balancing weight. So do the moment. That lets us figure out the B balancing weight. We essentially use the B weight to get rid of the moment, and then the A weight to get rid of any static imbalance that's left. Okay, it's a plug and chug. Just as long as you've got your position vectors, your masses, and your Z coordinates, and you've got your signs right on those, it's just a plug and chug. Watch your units on this. You're going to have, in this case, kilogram, centimeters. Centimeters are going to cancel out here, so you're going to have kilogram centimeters on the right. You're going to have kilogram centimeters on the left. You've got to be very careful with your units in this. Calculate your numerator and denominator here, and I get MB RBX is equal to this. So any set of MB and RBX that's equal to 0.329 will satisfy the X moment summation. Do the same thing in the Y direction. Again, it's just a plug and chug. Find your numerator and denominator. Any combination of MB RBY that's equal to negative 0.502 will satisfy the Y moment summation. So I need to find values for these now, and that will tell me everything about the B balancing weight. So in this problem, it just says dynamically balanced, right? It doesn't say, it doesn't tell me anything about how far the balancing weight should be, so I need to make a selection here. I need to let me get a little bit ahead and then I'll go back. So here I'm going to pick my balancing weights to weigh a kilogram. That's a choice. It's not specified in the problem. So usually what I'll do for homework or exam is I'll tell you I want a 1 kilogram balancing weight, or I'll tell you I want a 1 meter away balancing weight, and then you can find the other ones. But in this case, I'm just going to, since I wasn't told, and this would be more of a design problem, I'd say I can handle a kilogram for each of these things. So if I go back to here and plug a kilogram in for each of those, then RBY would be 0.329 centimeters. RBX would be 0.329 centimeters. RBY would be negative 0.502 centimeters. So I could solve for RBX and RBY right now if I knew that MB was a kilogram. So to do the A balancing weight, I need to go back to the force equations. That's these two. So I will go to the force equations. Note that for the force equations, I need MB times RBX. You already have MB times RBX. RBX is 0.329. So I don't actually have to solve for RBX and RBY, or what MB is if I know that the radius is, to do the force equation. All I need to know is the product of those things. So that's why I went ahead and did all of this in this one slide. Is I don't actually need to find what those RBX and RBYs are separately before I go back to these equations, because I know what the product is, so I just directly put that in there. And I can solve for MARAX and MARAY, those products. Again, this is a plug and chug, so watch your units, watch your signs, and I can solve for the product of MA and RAX. I can solve for the product of MARAY. Any combination of those, any combination of MA and RAX that's equal to product that's equal to negative 0.013 satisfies the static balance part of it. So again, just like with the B balancing weight, I can either pick the mass, say 1 kilogram, and I can solve for RAX and RAY, or I pick the radius, and then from the radius, I'll need the magnitude equation too. We'll talk more about that when we do force-based balancing. If I pick the radius, I can then use that in the equation for RA is square root of RAX squared plus RAY squared. If I know the radius, I can use this equation and these to find the balancing mass A, the A mass required. Again, in this one, I just pick the masses. That's the easiest cases where you pick the mass and find the position vectors. So I plug in 1 kilogram at each of these, and I solve for the location. I can then find angles just using arctan. Remember, arctan, you have to use arctan 2 on your calculator or on your spreadsheet to get your angles correct. That's a huge source of errors in doing this. That arctan function is dangerous. So here's where I need to put my balancing weights in this. And it'll be statically and dynamically balanced. Okay, force-based balance. The book does not do a good job on force-based balance, so I used an external resource here. You guys can see the link there if you want to see this PDF. But this is more useful. Force-based balance is how your tires are balanced. When you take them to a tire shop and they put tires on a balancing rig, this is what that machine is doing. If you're trying to balance a turbocharger impeller, this is what you do. If you wanted to make your own balancing rig, this is the math behind the scenes on it. So we're going to go back to our force summation, but now our external force is not 0. So what we're going to do is we're going to measure an external force, and we're going to use that to figure out what our balancing weights should be. So we're going to take the thing that we're going to balance. We're going to spin it about an axis. We're going to measure the force in 2 locations, and we're going to use that to infer the mass properties of how unbalanced the thing that we're trying to balance is. So instead of trying to figure out its geometry and its center of mass location and then balance that, we're going to build this thing, we're going to spin it, we're going to measure the force in 2 different planes, and we're going to use that to solve what our balancing weights should be. So I can take anything that I can find and spin, and as long as I can measure the force in 2 planes, I can balance it, which is why this is nice. It's because I can balance things that have already been made, and I don't need to know their mass properties. So why two forces? You need two forces. I've not tried the equation with one force. I have to think about that. You wouldn't get any information about the moment with just one force. With three forces, you could do it too, but it becomes unnecessary. You need more expensive transducers for this. So how do you measure these forces? They actually make bearings for the shaft that have X and Y force transducers in them that measure the forces for you, and they basically put probably some kind of a strain gauge amplifier or some kind of amplifier or some kind of sensor that's got an amplifier built in that just gives you like a 0 to 5 volts analog, or they make all sorts of different force transducers, but you just buy these things. They're a bearing that has an X and Y force transducer in it, and it just tells you what these forces are. Important thing to note here on sign convention of these forces. In this equation, this is the force on the body we're trying to balance. That's different than the force that our bearing transducer would measure. The bearing transducer would measure the force on the bearing. We want the force on the shaft. So for the purposes of this derivation and the problems I give you, I'm going to give you the force from the bearing onto the shaft. That defines the sign convention for those forces. So this is the force on the thing you're trying to rotate. The force on the thing you're trying to balance, not the force your bearings would measure. The force your bearings would measure would be the equal and opposite of the force on the thing you're trying to balance. It's important. That's why things might seem to be opposite of where they should be when you put your balancing weights on. It's the force on the thing you're trying to balance, not the force that you'd actually measure. All right, so we have the sum of our forces. We're going to use two of these, two forces, two planes to measure force. And then we're going to have the forces from our two weights we're going to add. Again, we're going to add a weight on plane A, which will define the origin of our z-axis. We're going to add a weight on plane B. It's going to be the force, the plane A weight will define our origin, and then the plane B weight will be somewhere over here, some z distance away that'll be known. We're going to have X and Y components for this, so X and Y components for this. We're going to solve for MARAX and MARAY in this, and we're going to get stuck here because we don't know what's going on with the B balancing weight. So we'll have to come back to this. We can use the magnitude equation. So all this equation is RA is the square root of RAX squared plus RAY squared with MA multiplied by both sides. This allows me to, if I know this radius RA, it allows me to plug all of this GAC in here and all of this GAC in here. And if I know RA, I can solve for MA required. So that's what, for the case where I know the radius and not the mass, I need this equation too. But again, we're not done yet because I need to deal with MB/RBX first. So we'll do a moment summation. So our moment summation, that's going to be R cross F from our origin, which is our A balancing plane. So we have R cross F for our two forces that we measure using our force transducers. And then the A balancing weight doesn't give us a moment about our origin, so it goes away. The B balancing weight does give us a moment. So we find the moment due to the inertial force from the B balancing weight. Again, that's the acceleration of this thing. This weight's trying to escape, so there's a force in the opposite direction that's going to give us a moment about that moment arm. So this is the moment due to the two forces we measure on our bearings. This is the moment due to the B balancing weight we're going to add. And we're going to cancel these out so there's no net moment. The sum of these is going to be 0, no net moment. We're going to split this into X and Y equations. We're going to solve for MB/RBX and MB/RBY on these. And I get MB/RBX is the sum of the Z coordinate for each of the forces times the X component divided by omega squared times the Z location of the balancing weight. We're going to get the same thing for the Y direction. Likewise, we're going to take the magnitude equation. RB is the square root of RBX squared plus RBY squared, multiply both sides by the mass, the B balancing weight, and I get this equation that lets me, given a value for RB, solve for the mass of the B balancing weight. What do I need to remember from this? I don't think I have a slide that's got all the important stuff boxed on this. So you start here with these two. Use this if you're given RB, and you can solve for MB, RB, MB, RBX, and RBY. You can solve for that given just the moment equations here. Once you have this and this, you can go back to this slide, these equations here, and you've got MB, RBX, MB, RBY. You've got those things from the moment summation. You can plug in here, solve for MA-RAX and MA-RAY. And then if you're given RA, you can use this equation. If you're given MA, you just divide this whole stuff on the right-hand side by MA, and you can find RAX. If you know MA, you can divide all the stuff on the right-hand side that you'll know at this point by MA, and you can find RAY. The easiest case is where you know the masses, and you're just finding the positions. Then you don't need this equation down here at all. If you're given the position and you want to find the mass, then you'll have to use these magnitude equations. So again, the stuff that's boxed, that's the only stuff you need. I'll do a quick example here. Our balancer spinning at 100 RPM. We have two bearings that are measuring forces in the X and Y planes. So we've got 6 pounds at negative 60 degrees, 4 pounds at 150 degrees. These are the force from the bearing onto the thing we're trying to balance. That would be the equal and opposite of what you'd actually measure with your bearing transducers. That's very important, that sign convention. Distance between bearings, 10 inches. We're balancing a wheel here, so distance from the rim, the left side of the rim to the left bearing is 4 inches, 7-inch wide rim, 15-inch diameter. So first step in this is to make a drawing. So it's 7-inch wide wheel, 15-inch diameter wheel. Our A balancing plane is going to be on the left side of the wheel. Our B balancing plane is going to be on the right side of the wheel because I can clamp material on there. Our first force we're going to measure is going to be 4 inches over here to the left. And then, so we'll be negative 4 inches this way, and we'll be positive 7 inches to, negative 4 inches to the first force transducer, and we're going to be, 6 inches from here to the second force transducer. We're going to be 0 inches to the first balancing plane and 7 inches to the second balancing plane. So this takes a little work to get a diagram in this case, but definitely you need to draw a diagram for this problem. We're going to do the moment first. So we're going to do the moment equations. We have two forces. So we're going to do the z coordinate for our first force times the x component plus the z coordinate for our second force times the x component of that. All right, so the z coordinate for our first force is negative 4 inches. Negative 4 inches. It is 6 pounds. We need the x part of it, so we want cosine of negative 60. So all of this is the z coordinate times the x component of our first weight. Z2, that's the z coordinate for our second force. That is 6 inches over, so plus 6 inches. And then the x component of that force, which is cosine of 150 times 4 pounds, divided by omega squared times z. Omega, now we've got 100 revolutions per minute. We need this in radians per second. Watch the units on this thing. I've got inches, pounds, inches, pounds, inches. If I got pounds and I put revolutions per minute in there, I'm going to make a mess. I need to get this thing in radians per second. So when I do that, I get radians per second squared. Radians are unitless, right? They go away. The inches divide out. I get pounds over second squared. I get slug feet. Just what I would expect to get. Mass and slugs, RBX and feet. Note that all of my dimensions so far have been measured in inches. At this stage, the inches here and the inches here will cancel out. But in this equation here, RBX will need to be in feet. And I need to convert it back to inches later on. You got to watch your units on these balancing problems. So it's very, very important, very common source of mistakes. The sign convention and the units will kill you on these. Do the y, right? So take the y equation, and only thing different here is sine instead of cosine. Real easy to put this into a spreadsheet. In fact, I highly recommend you put this into a spreadsheet, validate it on this problem, and you can do any of these things for homework real easily. Now I get MBRBY here. Just a coincidence that these two things are off like this. It doesn't always happen. Okay, so I want to balance this thing. Now, I know where my weight needs to be. The weight needs to be at a diameter of 15 inches. I can go ahead and find the angle. I can find the angle because I know MBRBX, I know MBRBY. MB is a constant, so if I use the definition of tangent, the y over the x, and multiply the top and bottom by MB, I can directly put this in here and this in here, and I can go ahead and solve for the angle. So I don't need to know the mass to find the angle because it's a constant in the numerator and denominator. It doesn't change the angle. So I can go ahead and do arc tan 2, right? Remember, arc tan, dangerous, bad. So I have to have the sign of both the numerator and denominator. I get 135 degrees. So that's where the B balancing weight needs to be. What's that angle measured from? It'd be measured from the positive x-axis. You'd have to do right-hand thumb rule on this. So for this diagram, it looks like what X would have to be into the page, curl up in the Y direction, my thumb would point in Z. So this would be 135 degrees from a vector going into the page with a positive convention for the Z-axis. Right-hand thumb rule, also important here. Okay, now this is the case where I have RB at 7.5 inches, and I want to find MB. 7.5 inch, that's again 15-inch diameter rim. This R radius is 7.5 inches. Slug feet, so I got to convert inches to feet here. When I do that, I just have one unknown, MB. So solve that out, I get 0.90966 slugs. So that is a tenth of a slug, which is 3.2 pounds. So I have to put a 3.2 pound weight on this thing. This is terribly, terribly unbalanced at 100 RPM. This is not a very realistic example. The numbers are way off from a real balancing weight. It'd have to be a pretty terribly balanced rim to need a 3.2 pound weight stuck on it. But anyway, we'll continue. So now I know everything that's going on for the B balancing weight. I know its mass, I know its angle, I can find its position vector then. Since I know it's at 7.5 inches, I can take that in this angle and find the position vector required for it. Then I can go do the force equation. There's a shortcut for this. The shortcut is I have MBRBX, so go to this equation and rearrange it and do MBRBX times omega squared, and I don't actually need to find RBX like I've done here. I just take the MBRBX I already have, multiply it by omega squared, and put a minus sign in front of it, and it saves a bit of time. So I've kind of done this the slow way here. So I have my force summation, so 6 pounds, this is for the first force, cosine of the angle, second force, cosine of its angle, negative MB omega squared RBX. But again, this is a waste of time because I already have what MB RBX is. I could just put that in. I could just put this negative 0.04272 slug feet times omega squared here, and it'd be faster. So again, just kind of a waste of time on this. Watch your units. Again, watch your units on all this. I'm going to be pounds here. This needs to end up being pounds on the right-hand side here. So this needs to be slug feet per second squared. Slug feet per second squared gives you pounds, right? So watch your units. And then down here, this needs to be in radians per second squared. And if I do that, I get slug feet for the units. So I have MARAX, do the same thing in the Y direction. Again, the only thing that's going to be different here is going to be sine instead of cosine. And then I've got the MBRBY. So this would be MBRBY. Go to the tangent equation. Again, that's tangent. The angle for the A balancing weight is going to be the Y component over the X. Multiply top and bottom by MARAY. So multiply both by MA, and I can just directly put these things in and find the angle. Again, 2-parameter arctan, I get negative 61.8 degrees. Use the magnitude equation. This is going to be up here at 7.5 inches. Convert to feet because I'm in slug feet. One unknown, MB. I I don't know, a 4-pound weight added. So this is a little squirrely. The numbers on this aren't exactly real world, but the process is, this is exactly how you would set up a tire balancing rig. The only things you'd have to watch if you're going to actually build this rig and do it, you'd have to make sure your force transducers would measure the force on the bearing. You need to equal and opposite it to get the force on the shaft for the way we've derived our equations. You could easily go back here and just put a minus sign in front of all of the forces and directly use the forces that your bearing transducers would measure, but you're still going to have to be careful about that. You have to be careful about your units. Some practical considerations. For tires, they're going to deform as they spin faster and their balance is going to change. So you probably would want to balance these things somewhere around like the mean speed for the mean angular velocity for a tire. That might be somewhere around 500 or 600 RPM, maybe higher, maybe lower, I don't know. But that would be the best way to ensure that it would be balanced. Or if you wanted it to be balanced at highway speed, take 70 miles an hour, turn that into the RPM for the tires. And if you balanced it at that speed, it's going to be balanced. Tires also deform when they roll on the ground, so that's going to change it too. So honestly, you're probably just trying to get it better than whatever it ends up being when you put the wheel on the rim. You're not going to get it perfect with compliant bodies like a tire. For something like a turbocharger impeller that's a rigid metal body that doesn't deflect very much, you're going to want to spin that up to the maximum speed it's going to be at in the machine and balance it at that to do the best job of it. Because what's going to happen as you spin this faster, these forces go up with omega squared, and you get more signal to noise on your transducers. So you're going to want to spin things up to their pretty close to their maximum allowable speed to balance if you want to do as good of a job. You're going to get more signal to noise on your force transducers if you spin things faster. For tires, they're so compliant and they deform on the road and they get bigger as they spin faster. It's going to be hard to do a perfect job. So you're really just looking for decent on tires. Turbocharger impellers, you need better than decent. You need a good job of this. So you want to spin it faster and get more force, more signal to noise. All right, that's it for balancing. I'll get a homework posted on this, and I'll do an announcement on Canvas about that for the due dates on it. So that's it for now. I will see you all later. Thank you.